Bea, please. Good afternoon, everybody. Now you have the fourth of the courses here, and it's a pleasure to me, though I know nothing about cosmology, apologizing for this, it's a pleasure to introduce Vivian Miranda, and I will tell you all that it's here about her life. I have all here. So, I can imagine that by now you know that she's from Rio de Janeiro. So one more of us here. I'm not from Rio, but kind of. She did the PhD here at University. Here, no. She did the master here at University Federal do Rio de Janeiro, physics department, I think. And then she did the PhD at the University of Chicago. After that, she was a postdoctoral fellow at the Pennsylvania University. And currently, she's a postdoc at the Stewart Observatory in Arizona, as you see there. The main expertise or interests are those that I list here. Dark energy, inflation, CMB, so cosmic microwave background, weak lensing. And she's a very active member of the Dark Energy Survey, between other collaborations, large collaborations she's part of. And there is a particular one that I would like to quote, that it's an incoming instrument or a NASA project that it's called WFIRST, and this is a project for a space telescope in infrared that will be launched soon, no? Soon. We say it soon because you never know, huh? It's, yeah, 2028. So, and another very, very important thing is that she was very recently, very recently received a prestigious, she was awarded a prestigious award, that it's Leona Wood lectureship, and that it's given for minorities that do important, very important results, no? For the important achievements of minorities in physics. So, there are two things here, the defense of all you can call these minorities, in addition of very, very important results. Otherwise, no award, no? So, congratulations for her for this. And this is given by the physical department of the Brookhaven Laboratory in US. And one more important thing is that she helped me searching for this, but I was like looking the number of citations of her posters, and there are those papers, there are those papers that are, from collaborations, and there are others that she is the main author, the first author. And the one that it's the most cited is one in theoretical cosmology, and this is related with her master thesis degree here in University of Rio de Janeiro. So it's very nice. She told me that she's not anymore working on this, but it's not the main thing she's working right now, but it's the most cited of her papers. So you should go and see. But now we'll have here, just to start, the fourth of the lectures, and this is about cosmology at the crossroads between theory and observation. So welcome, Vivian.
Hello, thank you. I think I know most of you. I was hired to give 4 lectures, but I want to maintain contact. So there is this WhatsApp group, my email is public, and I will provide you some homework that you are encouraged to do it, and you don't have to do it for tomorrow. You can continue working on that. and send me emails and make discussions on WhatsApp group. So let's make, a physics family group, but instead of political, let's talk about cosmology, and E&M. I think that I will be very impressed. And one thing that's important in academia that you should impress your professors because they write letters of recommendation. Okay, so I would like to start saying how happy I'm here. So there's this saying in Brazilian that a boa filha retorna a casa. So I like to think I'm a good daughter. So I started, as she said, I started going to UFRJ, then I went around, and it's glad to be back. And I know that a lot of people are saying bad things about students at public university, but I want to emphasize that I will be forever in debt by Federal University of Rio de Janeiro. So these are my Photoshop skills, very, very, very unique. And if it was not the excellent education that I got here in your institution at undergrad and master, I would never, ever have succeeded in the United States. So I will be, so whenever you call me, I never say no, and please continue to contact me. Okay, so let's start for Rio now. So the series of lectures, they have two purposes. So first, I will try to teach you the basics of cosmology, the easy part, in quotes, where, what's an expansion of the universe, what's a metric, how we observe distances in astronomy, which is a critical problem in cosmology. And then for the second part, I thought about teaching something that UFRJ doesn't have. So, I'm not sure if you're aware of, so UFRJ just hired a great cosmologist, Bruno, he's here. So please bug him, he's in the physics department. He has done great work, and he does large-scale structure. There's other people in UFRJ that are very good cosmologists, but there's no one that does the cosmic microwave background. And that was the reason why I left the country, because that's my passion, and no one in Brazil does that. So I will try to, introduce you to the concepts of the cosmic microwave background, and, so because I know that this is something that you won't be able to get, in his excellent course. Okay. So, as I said, the cosmology is kind of the science of the universe as a whole. So here we have great lectures about black holes, about star formation. But for us, stars and galaxies are just points in the universe because we want to see the universe, how it looks like in the largest of its scales. Yeah, you can turn off the light. I think it's better. So the type of the questions we like to answer in cosmology is like, what is the history of the universe? Is our universe expanding, contracting? How fast? Is the expansion decelerating or accelerating? How much non-relativistic and relativistic species there is in the universe? Does Doctor Who exist? Is this picture here? What dominates the energy density of a universe today? What about 1 billion years in the past? What about 10 billion years in the past? How the large-scale structures form, which is a lot of what Bruno researches. So this is the type of questions that are fundamentally different to most of you are used to, and that's what we do in cosmology. So I do observational cosmology, and Bruno can also attest this, that in observational cosmology, when you're in the bridge between, cosmology is a science that allows you to work in the bridge between theory and data. And that's excellent, You can do theoretical work, like I have published modified gravity, and I have published about, galaxies and how you extract signal from galaxies. So you can go back and forth between theory and data. But to do that, so basically to do that, it's important that in your education you focus on 3 different aspects of education, which I think actually is good in general, no? So it's important that you focus on your theoretical work and your physics modeling and the awesome physics courses that I'm sure you have. Then, we'll talk about statistics and how you use statistics to make sure that, your theory matches the data, and that involves Markov chains, tensions between data sets, Fisher matrix. And there's also a lot of data analysis, which is it's understanding the systematic effects that can prevent you to use weak lensing in the cosmic microwave background to extract information about our universe. We are in the era of this called precision cosmology. There's a lot of data. The amount of data, it's insane. Brazil is part of many interesting collaborations. Brazil is part of the Dark Energy Survey. Brazil is a member of the LSST, is a member of DESI, Brazil is building a 21 centimeters called Bingo, which will try to measure baryon acoustic oscillations. So Brazil is on these collaborations that you can participate, and you will see that in order to extract this information, there's a lot of technical details. So like what astronomers call signal, we call noise. What makes them happy makes me miserable. Usually it's like this, and that's why cosmology has to have this crosstalk to astronomers. And that's why I actually prefer cosmology group to sit in astronomy department rather than physics. Because, before I do cosmology, I thought I would never have to care about things like intrinsic alignments of galaxies. What is a blue versus red galaxy, where they sit, and you actually have to do. So there's a lot of interest in astronomy. And when you see that you have to know all of this, you kind of try to panic, like, okay, so do I have to be as good as theorist as Richard Feynman, and as a good as observer as, Adam Rees, and as a good of coder as the Facebook guy, which I forgot his name? No, it's not, So a lot of talking to theories, and talking to other people. Cosmology is not a science that you can do alone. You have to, interact, and you have to collaborate. Okay, so the first topic, so these are the survival rules of my class. So don't try to multitask because you're gonna get lost. Don't panic. I know there's this thing called math anxiety, and I had a lot of math anxiety in the past. So when you see a big equation, just breathe. We will go through them, so don't panic. And ask questions, especially at the end, okay? And especially in the WhatsApp group. Okay, so let's start. I like this because, Edward Hubble, the discoverer of the expansion of the universe, he did his PhD at the University of Chicago. That's the thing that I'm quite proud of. And his face is everywhere there. So he discovered in 1929 the expansion of the universe. So what that means, what did he actually observe? I will not show his data because his data looks like our experimental physics 101 data. No, it's so noisy. He just fitted what he knew what's happening, and if you see the data now, you can never believe it that he actually discovered. So I'm going to show like a state-of-the-art data, and in this axis here, it's something complicated, but basically, I'm measuring the redshifts, okay? We all understand redshift. It's redshifts plus corrections. Let's focus redshift. And the higher the redshift, the higher the recession velocity, and I will explain why. We will kind of reveal the Doppler effect. Here is magnitudes, but I will translate this magnitude to distances. And I will explain how I can do that, because we know that in astronomy, you usually cannot translate magnitudes into distances. And the idea is that the further away you are, the higher is your velocity of recession with respect to us. So we are moving apart at some speed. We are, with you, we are moving apart at higher speed, and there's a linear relation. So everyone that's around us, on average, is going away from us, and has this linear power. The further you are, the faster you are. So that's the theory, and that's the discovery, the expansion of the universe. And you can extend. You can try to do these experiments where you put dots on a ball, and you inflate the ball, and you see that all dots go apart from each other. But here's an astronomy department. So let's go a little bit technical. How quoting distance is easy here. So I can measure this distance. But how do we extract distances in astronomy, and how we extract velocities? And that's important because some of the most difficult problems in cosmology are related to two basic problems. How do we measure distances, and how do we weight the universe? Okay? So let's start with magnitude. So this is apparent magnitude. I assume you all know what an apparent magnitude is. It's this weird scale that it's a logarithmic scale that, negative means that every time you go one apparent magnitude, you are 2.5 times more brighter. And the question is, does magnitude provide us distance? If I just measure the magnitude of a star, can I figure out what is the distance of that star? And the answer is usually no, because we don't know what's the intrinsic brightness of stars. If you see two stars and one is fainter and the other is brighter, it could be that the fainter one is more distant, but it could also be that the stars are at the same distance, but they have different temperatures. So that exemplify how hard it is to measure distance. And here I'm just putting like 2 different temperatures. And we know from the black body radiation there is a relation that between temperature and brightness to the 4th power. So the brightness depends on the 4th power of temperature. So we have this problem now. If they have the same apparent magnitude, are they same distances or are they different temperatures? So in order to extract distance from apparent magnitude, you need an object you can calibrate. You need an object that you either know its absolute magnitude, in case you can extract its absolute distance, or you know how to compare them. So if, for example, one object that we use in cosmology a lot is the Type 1a supernova. Here's one of them. And this is an object that we don't know its absolute magnitude. People make that mistake, and that creates problems in cosmology. What we do know in Type 1a supernova is that if given the spectrum and the light curve of 2 supernovas, we know how to do a relative calibration. We know how much one supernova is brighter or fainter than the other one, but we don't know its absolute magnitude. There is a constant there, and it's the most important constant in cosmology that we don't know, which is the Hubble constant, and I will explain this. So, okay, so these are the Type 1a. I will not explain what the Type 1a supernova was. Basically an explosion of a white dwarf. And as I said, we only have relative amplitudes of a supernova, so we need also other calibrators. So one calibrator that's heavily used, and this is real state-of-the-art Hubble data, it's called Cepheids. And Cepheids are these strange stars. So, I always had problems, understanding how well behaved are Cepheids, where they clearly oscillate. So this is the brightness of many Cepheids with the Hubble telescope, and you can see that there's an oscillation in brightness. The Cepheids go up and down, and it's almost a miracle, but the important thing about Cepheids is that the period, if you know the period of oscillation is related to its absolute magnitude. So here, there's these relations between period and luminosity that are quite tight. Whenever astronomers tell you a linear relation, it's basically not linear. You see the spreads in their plots, like it looks like linear, but there's so much errors, and we have actually some of these plots today. But these are really tight. Now, this has a small spread. So Cepheids is another way that we can calibrate distance, but to do that, we have to see individual stars, and that's hard because we don't have good telescopes to see individual stars that is like a gigaparsec away. There's a third one, and this one is actually the only one that you can actually get absolute distances, which is parallax. Now, probably you already, astronomy 101, that Earth goes back and forth during the year, and if there is a nearby star, this actually changes its angle towards the background stars. And what I like that this is the real parallax observed in Proxima Centauri. Proxima Centauri, yeah, the star that's closest to us, and you can see that there's 2 movements here. First, the star do this, and that's proper motion, and they also go back and forth, and this is parallax. And that, if you know parallax, you can determine the distance of star, and that's very important, and that's why we have Gaia. That's why Europe just spent millions of dollars in this new telescope to measure parallax of stars. So what we do in cosmology, usually we build a ladder. So we have these distance indicators that, that works in different regimes. So for example, parallax, you can only determine distance that are, relative close. But we have this regime here where we can calibrate Cepheids with parallax, and then you go to Cepheids that can give you this regime. And then there is Cepheids, you can determine, from Cepheids you can calibrate supernova, and then you can determine supernova. So that's how you determine absolutely distance. And that's important because people have asked me, okay, people say that supernova is a standard candle. If it's standard candle, why we need to calibrate supernova? Why it's so hard to get the Hubble constant? That comes from the fact that supernova only measure relative distances, not absolutely one. To get absolutely one, you have to do this. And this is and once you have that, you have absolutely distance. You can get the distance redshift relation, and you can get the amplitude, the slope of that relation. And yeah, and get slope of that relation. So we know now how difficult this axis is. And I want to come back to this plot and now look about this one, redshifts. How do you get redshifts? And that comes from the fact that when you see the Hubble ultra deep field, when you see the universe, in its largest scales and as deep as you can, you see the universe is red. Okay? So basically, boys are blue, girls are pink, universe is red. Okay? And to see this now, there's this set of like the most distant galaxies, because these are not stars. You cannot resolve stars at those distances. And you can see that are pretty red, So here is actually the most distant galaxy in the Hubble ultra deep field, and it's so deep that you don't see even in red. You see only in infrared. Okay? So why the universe looks red? It looks red because of the Doppler effects. Remember that the universe is expanding, things are going apart, and the faster you go apart, if you have a relative velocity, you have the Doppler effect. So let's remind us about the Doppler effect. So basically, you have here, and you emit a signal to me, and this is Earth before humans, quite before humans. So you emitted the signal for the galaxy and has some particular color or wavelength. But as this propagates, the universe is expanding, and in particular, the space between peaks and troughs in this is also expanding. And that is in particular, because of this expansion, this wavelength is getting larger, and this is the concept of redshift. So, and we are humans, we are very limited, so we see a very limited range in the E&M spectrum. So we see a less than a factor of 2 in terms of wavelengths. So, if a galaxy is blue and the universe doubles its size, that's enough to make a galaxy red. So you don't have a lot of you need a lot of expansion. And in fact, so here is just the formulas. So we know the classical formula of a redshift is the observed wavelength minus the emission over the emission. And I will show you that there is a function that tells how much the universe is expanding. That's the scale factor. And the scale factor can be directly related to redshift of light that comes towards us. Okay? Everyone's on board. Did you jump the mothership? No. Okay, good. But now something interesting. It's like what I love to study and what made left the country is the cosmic microwave background, which is what? A microwave, by definition, which has a wavelength of a few centimeters. Okay? So, and then you ask the question like, when the cosmic microwave background was emitted, we will talk about this in lecture 3, but how much the universe expanded system. So we like to talk about in terms of E-folds, which E-folds basically, you take the exponential and whatever is here is the E-fold. So the universe had 7 E-folds of expansion since the emission of a cosmic microwave background. And basically, so if you take this and you blue shift in the past 7 E-folds, you got something that's red. So the universe, when the cosmic microwave background was emitted, was actually emitting the optics. The whole universe looked like a big star. But the universe has expanded so much that now we see those flashes of Big Bang in the microwave. In the future, we will see radio waves. Okay? Good. So now we know how to do this. This is easier. This is hard. But when you do this and you try to see what is the slope of this, it's called the Hubble constant, and it's the most important constant in cosmology. Although it's a kind of a local measurement. It's far. It's not that far. And that's the concept we don't understand today. Like, what is the biggest problem in cosmology today? Bruno, what's the biggest problem in cosmology today?
Biggest problem?
Yeah.
Systematics. Dark energy.
Yeah, and dark energy predicts a value of this constant that is 4.5 sigma away from what we observe. 4.5 sigma, even, astronomy is like, everything above 1 sigma from astronomers is cool. Like, yeah, it's attention. Now, particle physicists, they have a higher standard. Their standard is like 5 sigma. We are almost at the standard of particle physicists. Okay. Another interesting thing is how hard it is to measure this. So here is the date from like Hubble to today. And you can see that, and there's also, you can see something that are also very interesting. Now, this changed by an order of magnitude. but nearby points are close to each other. This is a sociological bias in science. Now, if someone that is good in science measures 100, and you come from Federal University of Rio de Janeiro and you measure 80, you say, no, I cannot be 80. So I will tweak, I will hack my data to be 100 because Adam Rees published 100. Don't. Trust yourself, because this happens. That's why you need people that are important to die, so you have the courage to measure it correctly. Okay, and if you plot a lot of measurements in science, that has this effect. Nearby points are close, even though the techniques has changed a lot, and long baselines are different, because so have courage. Science requires courage. Good. So that's the introduction. Like, we know now the universe is expanding, and I will follow a classical mechanics a book that first talk about the kinematics of the universe, and there's dynamics. I know some of you has like classical mechanics, and there's a and they're quite traumatized. So please, forgive me. I will try to make you like classical mechanics again. Okay, and I now require you to know general relativity, although you should learn general relativity, but I will introduce you concepts of general relativity, because our universe is a curved space-time, so you need to know a few things to do cosmology, not much. Okay, so what is the main idea of GR? Main idea of GR is that gravity is actually a change in space-time, and that if gravity is the only force, everything is going geodesics in the shortest distance between points. Because gravity is really a force. So here you can see a comet. For a comet, what is the equivalent of a straight line in this geometry is actually a curve. And that's the curve that things follow. So there's two aspects of general relativity. That's why I call kinematics versus dynamics, is that first, you can calculate how the sun produces gravity, how the sun changes the space-time. That's dynamics. Then once you give this space-time, you can ask how the comets and Mars go through these space-times. That's kinematics. And I will start with kinematics. I will tell you like this is the metric, and this is how we go to this metric. Okay, so but in cosmology we don't have comets or planets, we have galaxies. So these are galaxies, and these are their pathing time. And even though it's a space-time, in universe you can actually slice it in space and time, like we did in Newtonian physics. So these are spatial slices, so constant time, and this is evolution in time, and this is another spatial slices. So these are the geodesics. So these galaxies are through gravity. So this is actually geodesics. So general relativity means that this geodesics has some dynamics. And so what can we do with a geodesics in general relativity? We can do three things. You can make this geodesics expand isotropically. You can make this geodesics to rotate. Mario Novello loves those rotations. If you do cosmology CBPF, I don't, but you can make this geodesics rotate, like in a black hole. A black hole, the geodesics is rotating. You can also create shear between those geodesics. Okay, so theoretically that's what you can do with the geodesic. But we are very lucky that we live in a universe that has symmetries. Symmetries is everything in physics. So what is the symmetries of a universe? So here I'm showing actual data that's not simulation. So what people call galaxies that's very large, it's a point in this plot. There's like millions of galaxies in this plot. And this has 2 gigaparsec, and this has 1.3 gigaparsec. I like astronomy because they call like parsecs or a few light years. It's very far. No, it's like our neighbor. This is very far. And you can see that there's a distribution of galaxies in the universe that looks more or less, not completely, but more or less isotropic. You don't see like an axis like empty, and the axis of God, like with all the galaxies in it, Or you don't see a shape like an eye and a creepy like smile, and all the galaxies are in this smile, like the smile of God. No, you kind of see that more or less is homogeneous, more or less like noise, although there is voids and there is clusters of galaxies on smaller scales. That's because our universe is on average isotropic. Okay? So that we can actually show through observations. But then we have to make a philosophical question, because there's a two-way a universe can be isotropic. You either at the center of it, Bolsonaro would love to be in the center of the universe, okay? Or the universe looks like isotropic in every point of space, and therefore the universe is also homogeneous. We cannot prove the universe is homogeneous, but it's a philosophical choice. There are questions. No, not every question that we invent, can be answered by science. Now, that's one that we have to choose. It's an axiom. So we axiomatically will say the universe is actually homogeneous. So if it's homogeneous isotropic, then the only thing you can do to this geodesics is isotropic expansion, the expansion of the universe. You cannot rotate, you cannot have shear, and that makes our life much easier. Okay? So GR is the most difficult topic in physics I ever encountered. GR in cosmology is actually quite nice because of the symmetries. Okay. Questions? Let's pause. I have talked a lot. Questions so far? Here's a question. Sorry. Come on. You're already trending, so ask the question. No? You can ask in Portuguese and I translate. Come on. What's your question? Isotropic is something that looks in every direction. So like this direction looks exactly like this direction, but this direction looks different than this one. That's not isotropic. Isotropic is something that looks the same, and that looks kind of the same in every direction. Good. More questions? Yes. Shear is like walking in a honeymoon. Okay, I hate Aquaman. Okay? Aquaman sucks. Why it sucks? Because they are in water. Water has shear, and it was like, dun, dun, dun. Have you tried to move in water? It's like, oh, I want to die. That's moving water. That's shear. You know, it's making difficult, for you to go through. If you can reduce shear by having these extra suits that will reduce the shear, and then you can move faster. Never like Aquaman, but I watched Aquaman when I was from a neighbor in the airplane coming here to Brazil. I was like, this is so bad. Okay, so yeah, that's shear. Now, when you move in a honeymoon, that's shear. It's the shear between the layers of a honeymoon that makes the honeymoon look like almost as a solid. Okay? Questions? Okay. So there's no shear, nor vorticity. There's only isotropic expansion. The universe looks like this, and it can look like that. So, but every direction will still look like isotropic. So that's what's called the scale factor. There's only one function that's there's two numbers that are important in the kinematics, but the dynamic ones, the scale factor, it will tell how the universe expanded isotropically. Okay, and that's called the Friedmann-Robinson-Walker geometry. There's also Lemaitre, but then it becomes too big. I'm not a historian, I have a friend that do history of science. He wants to kill me if I don't put everyone that they created. It's just FRW. Okay, good. There's one more thing you can do in an isotropic homogeneous metric. You can determine the geometry of the spatial slices. So we know that this, in time, they expand. But there's geometry here. So let's see this geometry in terms of a triangle. So we learned, I hope, I didn't, but we learned that that if you sum a triangle, there's a fixed number that's 180. Usually, I think I learned at some point to prove that, but basically I believe it's an act of faith. So this is the plane geometry, but there are other types of geometry where this angle is actually not 180 degrees. If you live in a sphere, they actually sum more than 180 if you take a triangle in the sphere. And if you take a hyperbola and you make a triangle in a hyperbola, it actually has less than 180 degrees. So what you have to decide in this spatial slicing is what is the sum of all angles of a triangle? Is it 180? Is it larger than 180? Or is it smaller than 180? That's a choice that we have. So these are the two choices we can have in a metric. We can have the isotropic expansions and the geometry of spatial slices.
If I did understand what you are talking about, we can't separate time from space. So that means we have a different geometry for every instance of time.
These actually, the one on spatial slice is actually fixed. You know, if it's 180, then it's larger than 180 ever. Now, this choice, once you make it, it's set. But the geometry changes because of the expansion of the universe. But that choice actually doesn't. No, it won't. You make a choice. If you create a universe, you make a choice, stick with it. Okay, good. So let's try to understand a little bit of the geometry. So let's pretend we live in a sphere. We live in a surface of a sphere. So this is Earth, center of the universe, as humans like it. Okay? So these are two galaxies, you know, and I didn't know if you prefer, you know, blue or red galaxies, so I make a spiral and elliptical galaxies. And so they emit your light. So how this light will propagate in a sphere? It will propagate towards the geodesics of a sphere. And the geodesics of a sphere is this. So the radial one is the light will propagate to this guy, and the light will propagate to this guy. Okay? So there's an angle between them. So let's pretend that for some reason we actually know this distance between these guys. We want to figure out how these galaxies are apart, are in the same cluster, or they're billion of light years away. So if you want from this angle to get this length, we have to know something that's called the angular diameter distance. And if you do the geometry of a sphere, you will see that this guy here, if you just propagate, no, the r is the radius of the sphere, you see that this radius here is less than the radius of a sphere. There's a sign here. So to go from an angle to a length, there's a sign, and there's a radius, and this radius is less than the radius of a sphere. So it's easier to convince yourself that, you know, if you kind of have the latitude, the angular diameter distance will basically be the distance, the radius of the sphere times sine of this ratio here. D versus R, the ratios of the sphere. And therefore, and the sine is always less than 1. So that means that objects in a sphere, they always look closer to each other than they will look like in a plane from the same angle. Okay? So in a sphere, you have two distances. We have the distance of the radial distances, and we have angular diameter distance. And they are not the same. And it's important to visualize this, because whenever in cosmology we say that distances are not the same in cosmology, we have luminosity distance, angular diameter distance, people just freak out. It's like, why? How? This is an example. Okay, so, and now we want to say how I can propagate myself in a sphere, how I can measure distance in a sphere. Well, we can measure distance in a sphere by measure distance along the line of sight and distance perpendicular to a line of sight. So your distance indicator, like the length of your path, is line of sight plus perpendicular to line of sight. And basically, this is the Friedmann-Robinson-Walker metric. That's what makes the space not plane. And once you have this, the only freedom you have, the actual freedom you have, is to expand the sphere. The sphere could be small, and then it can be expanded, and then you multiply this by a scale factor. That's the Friedmann-Robinson-Walker metric. So the universe it expands, you know, and then you can have, so you can, and the expansion of the universe will change the initial distances you had. So you can also take the initial distances that you had here and multiply by a scale factor, and it will continue to increase because the universe is expanding. But using in cosmology, we take that out, these factors, and we call this distance here the comoving distance, and it's called the physical distance, and that's more a technical difference. What about this guy? I saw that this guy is another option, and to get this, you basically have to make your radius imaginary. That's how the mathematics work. And in this case, the angular diameter distance is the sinh, not the sine. Sinh is always bigger than 1, if I remember correctly. So you always look further apart than you actually are. So that's the first don't panic. So that's the first slide with more equations. But what I explained to you is that basically the Friedmann-Robinson-Walker have a difference between distance along the line of sight and distance perpendicular to the line of sight. And if you want to do 3D, you just have to change an angle by a solid angle, and then that's the metric. That's where we are going to be the kinematics. You can be volume elements. That's the distance times the distance along theta, the distance along phi, and that's actually an important detecting volume in cosmology is an important problem. So people, for example, use countings of clusters, the density of clusters, to try to probe dark energy, for example. And that's it. That's what a Friedmann-Robinson-Walker metric. You all learn now how to do GR. So any questions? Do you understand the geometry of a sphere? It's okay. Okay. Then you say, Vivian, you just smoke weed, because I happen to open a cosmology book, and the Friedmann-Robinson-Walker, it's not this expression. It's some crazy expression that looks nothing like this. And I say, because they are lying to you. They are manipulating you. So it's kidding. So what they want to do in most cosmology books, they want to write something they want to write the Friedmann-Robinson-Walker such that the distance that you propagate along the line of sight is also the angular diameter distance. So there is a simple trick that you can do. You can change your variables so that this guy is the dA. Just make some signs, and then you transform this guy into this guy. And that's what usually there is in cosmology books, where you have these constants, and these constants can be plus, minus 1, or 0. Okay? It looks complicated, but it's just a change of variable from that simple equation that we derive in a sphere. Okay? First time I learned this was at the University of Chicago, and my mind blew. Like, oh shit, this is so cool. All right? So now you have intuition on the Avogadro metric. Okay, so this is like the end of this exercise. You can write the Friedmann-Robinson-Walker in two ways: the intuitive ways, and the way to pretend you're smart. So that's what people usually do in books or in your class. But it's usually basically this more intuitive way that you can actually draw in a sphere. Have you seen this before? Yeah, nice, isn't it? Okay, good. Okay. So another thing that that's important. There are questions so far. Are we surviving? Okay.
Sorry.
Yeah.
This equation is, I don't know if it's a coincidence, but similar to the Pythagoras theorem.
Yeah, but in curves. Yeah, in curve
Yeah,
space.
but it's just a coincidence or something like that.
Yeah, so the choice is between those geometries is if Pythagoras works or doesn't work. It's with a smaller. Okay, so another thing that people talk a lot in cosmology is called conformal time. So actually, I think we all know have special relativity. I assume this. And in special relativity, you have this, your full space-time metric has a time component, and the spatial component has a negative sign. In cosmology, you have some similar thing. You have a time component that we write this way, and the spatial component that we just derived. So that's like the four-dimensional Friedmann-Robinson-Walker metric. Looks like a lot of GR, except that you all have this scale factor here. Okay? So one thing that we learn in special relativity is that photons travel in no geodesics. Do you remember this? Okay, so what's a new geodesic? New geodesic is this equals 0. So for a photon, there's equivalence between space and time. There's a C factor. These are the two ways to create this. And then you can ask your question like how much distance you travel, which is equivalent to how much time you travel, and that's related to the scale factor. I don't want to go too much in details here. So, except that once you have this expression, you can ask yourself, what is the maximum distance photons can travel since the beginning of the universe? Can photons travel infinitely far? And the answer is no. And I will tell you something that will blow your mind. So since the first second of the universe, photons can only travel 2 degrees in the sky. 2 degrees. So it looks like a miracle that the universe here and the universe that's 90 degrees away looks the same. Because photons that comes from here have never connected to photons that comes from there. And that's was a big problem in cosmology until recently, and that's something that's solved by inflation. I will not talk about inflation, I will just give you this problem. If you calculate this, you get something that's around 2 degrees. Okay, I will skip this. No, yeah, okay. So you have distances, and it's relatively simple to change, to transform distances to redshift. And yeah, and this is from the Hubble function. Sorry, I got a little bit lost here. So okay, so you can calculate distance in terms of time, because distance in time is the same for a photon, because it's a new geodesics. Once you have time, you can correlate time to scale factor, which is how much the universe expands. And scale factor, remember, is related to redshifts. And the relation is the Hubble function, is the Hubble constant that evolves in time. So a big thing in cosmology is what's called the distant redshift relations. We would like to, which is exactly what we measure. We would like to, measure redshifts of objects, measure their distance, and if we know their time, the redshifts, and their distance, you can determine the scale factor, and you can determine how the universe expands. Okay, so how do we detect redshift? So in type 1a supernovas, we detect redshift through silicon lines that we observe. So this is a supernova that has like a week since explosion, and this is the redshift of the silicon line, and you can compare this redshift that's observed to redshift from the ground, from the laboratory. We do have an astrochemistry here. Where is she? She's doing exactly this. She's measuring lines in the universe and comparing it to lines in the lab. Isn't true? So here is some lines in the lab. I love this plot. There's iron, calcium, silicon, oxygen. So when you compare that, you can get the redshift of objects. Okay? And I'm saying this because this is the table that gave the Nobel Prize to Adam Rees in 2011. And what he did basically was measuring the distance of supernova through magnitudes, getting the redshift, and from that relation, distance to redshift, he reconstructed the Hubble function. And through that, he discovered the dark energy and discovered the accelerated expansion of the universe. And that's what I'm going to teach you in next class, how to exactly do this. So getting distance redshift relation is one of the main topics in cosmology. And for that, you need to calculate redshifts, and you need to have standard candles. Questions, come on. Are you okay? Good. So this is like the basics. But there's a technical point that I want to point out, which is that the concept of luminosity distance. Like if you observe a supernova, how do I extract distance from it? And is this distance given by this d here? And that's an important question because we knew, for example, that radial distance are not the same as angular diameter distances. So if you measure distance from flux of objects, now, is this the same of this radial distance? And the answer is no. So let's do this exercise. So this is a real supernova that we use in cosmology. So we want to get the distance relative relation, and we observe the flux of this guy through a telescope. Okay? So what is a flux? So basically you point your telescope here and you observe the energy that's emitted to the supernova by unit of time, by unit of area. Okay? If you can resolve the supernova, you have the area, you have the solid angle. And I would like to convince you that all these factors are impacted by the curvature of the space-time, are impacted by the expansion of the universe. So let's go through how. So first, there's energy. So we know that things are getting redshift as it expands, and red light has less energy than blue light. So energy goes down as the universe expands. Area changes in cosmology because the angular diameter distance is different than the regular distance. And area is basically 4 pi angular diameter distance square. A more technical term here is that time also got dilated in cosmology. So basically, if you have a wave, so let's go through here. So a wave, a light wave, is basically a wave like this. So the supernova emitted here, and there's emission here. So you detect the wavelength through these 2 times. And these times between a trough and a peak, a trough and a peak, gets dilated by the space-time. So I have this calculation here that show how it gets dilated. I will not enter in details. So when you put everything in perspective, you actually get that the luminosity distance has an extra factor of redshift with respect to the angular diameter distance. So that's, if you know these technical details, you can actually, figure it out how to get the luminosity distance redshift relation. Okay, questions? 15 minutes, okay. Almost there. Almost done. Okay. So basically, okay, so we do this to the concept of magnitude. So we all know magnitude. I like this table for magnitude from the 1700s. So we measure the flux of supernova, the terms of the magnitude, and from magnitude we determine the luminosity distance. And the luminosity distance depends on the expansion of the universe through a relation that that is 1 plus z plus times the distances. Okay. Let's skip this. So what you actually have in this table that won the Nobel Prize is the redshift times the magnitude, the difference between relative and absolute magnitude, which is this formula that you learn in astronomy, that 5 times the logarithm of the luminosity distance divided by 10 parsecs. So when you do Astro 101, you get the normal distance here, but as the technical detail, you get the luminosity distance. And I would like you next slide to teach you how you get these 2 numbers here, mu and z, and you discover dark energy. Skip this. Another problem that I would like to talk that's more interesting is the Albro paradox. That's pretty cool. Before it was a little bit too technical, but that is actually something that is really cool. Why the universe looks dark? Why there is day and night? That was a problem that cosmology took 100 years to solve. So why there is day and night? Tell me, come on. No, but okay, but in our day, like why do we think there is day and night if we don't think about the universe as a whole? Yeah, because there's a sun and Earths rotate, okay? But what yeah, rotate. But I will show you to tell you that in the 18th century, we thought the universe was infinite, okay? And an infinite universe with a lot of stars. And then I will tell you something that will blow your mind. We know that the flux of a star depends on the square of the distance. If you double the distance, you divide the flux by 4. But the area that you go in the sky also increased by the square of the distance. So in the universe of the 18th century, these 2 facts cancel, and the contribution of all stars in the universe should be equivalent of what you get from the sun. And I have a simulation for that. This is what the night sky should be. You see that I'm getting stars that are fainter and fainter, but when I sum all them up, the night sky should look exactly as the daylight. It took us 100 years to solve that problem. And remember, the source of the problem is that flux depends on one of the square of the distance. Area depends on the square of the distance, and they cancel out in a flat universe, but they don't cancel out in an expanding one, because there's these factors of redshift that I took many slides and you almost left, because, it's boring. But those redshift factors is what save us from burning during the night. Because when you put them into account, you get a factor of 1 plus e to the 4th, and that's why the night is dark. and light and, huh? Yeah, for terror, yeah. You know, whenever I saw Batman versus Superman, and it was like light versus dark, you know, night versus day. But, you know, that's why the night is dark.
The solution of the Olbers paradox before it was discovered that the universe expanded. I remember there was something Edgar Allan Poe said, even.
Yeah. So the Olbers paradox depends from the fact that you have a homogeneous and infinite universe. Our universe also is not infinite, so there is not infinite number of stars that actually help. But, you know, today we know, like, it's a mix of universe is not infinite. Sorry, the universe is not infinite in time. It's not homogeneous in time. It's not static. So there's evolving number of stars, and there is this factor 1 of times redshift to the 4th. Like, it's amazing that some simple problems take so long to solve. Okay, so this is kinematics. This is everything I have to talk about kinematics. You know what's a metric. You know how to calculate distance from flux, distance from angle, distance from radial propagation. You know the concept of redshift. That's like half of your cosmology book gone. Okay? And some of these derivations are technical, so go through the slides after this talk. Ask me questions, you know. Try to, you know, make sure that they look reasonable. Now it's dynamics. Dynamics is how the scale factor evolves in time. Now, how GR can make things evolve in time. And that's the concept of general relativity. Now, this is what we got from Einstein equation. I ask you to do exercise. Download Einstein's paper, the Einstein equation. It has 3 pages. Like, it looks like this. There's like this, you know these crackpot papers that it has like 3 pages and you're like, this is crap. No, I'm pretty sure like most of the science that read that paper might say, oh, this is crap. This is like crackpot. 3 papers is simple now. You don't have to write a lot. So if your paper has more than 20 pages, think that Einstein had 3. Okay? So the concept of general relativity is that, you know, matter and energy creates space-time. Space-time makes matter move. So this is the equation where matter creates space-time, and this is the equation where space-time makes matter move, which is the conservation equation. So there's this cycle that, you know, matter tells geometry how to curve, geometry tells matter how to move. We have gone through this part, and now we are going through this one. And the way matter makes geometry move is through the first Friedmann equation. The Hubble constant and how it evolves in time depends on the amount of the matter you have. And here is like the density of dark matter, the density of dark energy, the density of radiation, plus a factor here that depends on this geometry. If it's flat, this factor is 0. But it can be, if you have a curved universe, you have this extra factor here. How much time I have? Because I can go 2 or 3 more slides. Okay. Yeah, I can do 30 slides, depending, you know, in 6 minutes. Okay. So this is how GR makes matter go through, geometry depends on matter. So there's a trick you can do. You can define the curvature as an effective density, like this, and you can write this guy as a sums of density. So let's do this. And I have 3 more slides, and I want to finish with something that will blow your mind again. So I would like to write this Hubble function as the sum of real density times this curvature density that depends. And when you sum up them, they all depends on the critical density here. So there's a critical fact that, you know, a universe that looks like a sphere is a universe that needs to lose weight, like myself, because there's a universe that has too much energy density, has an energy density that's more than the critical density. Okay? So that's a universe. But why? Let's prove this. It's because the following. If this is bigger than this, then this needs to be negative, and this is minus a number square. So that's real radius. Okay, so if it's the contrary, it's like my sister. I also try to give, my sister is very slim, so I try to give her food. So it's like my sister now, I try to feed her. So you have less than critical density. then this guy needs to be positive. The only way you can make r squared minus 1 over r squared to be positive is r is imaginary. That's this geometry. Okay? And you can be flat, where you exactly at the critical density, then you don't have any geometry. So that's a very special case, and that's the case of our universe. Why? Why we have such a special case? That's another problem that inflation solves. You can calculate what is the critical density, and you get these big numbers here. And then I'm going to show you something. Whenever you get a big number you don't understand, you have to make an example to understanding. So the critical density of the universe is 10 to the minus 29 grams. That makes no sense to us. We don't have, there's no 10 to the 29 in our brain. So I make the following exercise. How much drops of water I have to put in Earth's volume to have 10 to the minus 29 grams? And the answer is 180. So 10 to the minus 29 grams is you get the volume of planet Earth and you put 180 drops of water. That's something you can understand. That's what Feynman did in his book. Say, take a big number, make understandable. So the density, the critical density of the universe, which is the actual density of the universe, is 180 drops of water at every Earth's volume. And I can stop for here and continue next time.
Questions? Okay.
Well, you talked about a spherical universe, right?
Spherical, yes.
But matter curves the space-time.
Yes.
So the distribution of galaxies in the universe can change that spherical.
Yeah, it does.
Geometry.
So that's perturbation theory. So for now, we are doing background. So I'm assuming the universe is really homogeneous and isotropic. How, you can go further and you can calculate linear perturbation theory, non-linear perturbation theory, which is exactly how halos and these voids and halos tweak that sphere. And that's something that I actually do a lot. So that's next step.
You understood all of this?
Yes.
No, I do have a question, if you don't. My question is very basic. When you were showing the scale of distance, so you showed the supernova one way and the other bases of the scale, and there was there in this plot till which redshift you can get with the different methods, yeah? But it wasn't possible to see. I think that this is, it's a thing that I have a mess here. So
yeah, so I don't, parallax is just Gaia. Gaia is like, I don't know, like 100 parsec, 200 parsec. It's like very small. Now, yes, no, we can get parallax of the large margin LMC. I think you can. Yeah.
Is that true? Is that true?
No?
I don't think so. Not that large.
No, yeah, sorry. So what we do, okay, I just remember. So, but there are lots of Cepheids in the small volumes that we can get parallax. So you can calibrate with the Cepheids nearby. Then you apply this to the Cepheids that are further away, like in LMC, you can observe Cepheids there. And then, and because something that I want to show that, supernovas are rare. So it's like one supernova per century in our galaxy. So you have to get more volume to beat this. And nature is not, we don't live in string theory, so we don't have 15 dimensions, but we have 3. So there's a power of 3 in distance that help us. So, if you want to have 8 times more volume, you just have to go twice as far. So basically, the Cepheids help us to go far enough so there's enough volume that we can observe at least a few supernova per year. So that's, and there's a calculation, it's basically redshift 0.01. So, 01. CMB is at the redshift of 1,000. So let's just give you a difference in scale. Huh?
If you put in that scale, for instance, the method Franz was saying this morning that using quasars, So this would be till
This is
whatever.
redshift 2 is like, yeah, no, that's like in that scale, quasars are like in Sao Paulo. No. Yeah.
So any other question?
But
Please
you
come on.
can, yeah, so we can scale. So, because supernovas, you can observe supernovas up to redshift of 1.5 or 2. So from that, you can actually build and get the actual distance of quasars. You know.
Hi, and I didn't understand the light travel example of 2 degrees on the primordial universe. Can you explain?
Yeah. Okay. Yes. Can you? I need lights.
Not due to the expansion of the universe. Why?
Yeah. Okay. Okay. So let's remind. What's angular diameter distance? Is suppose you know the length of something. I want to determine the length of something. So for example, so you are here, and you have something that has this length lambda that you know. And there are things in the universe that we know the length. For example, that's the baryon acoustic oscillations. So that's something that, so you know this. Suppose you know this by magic, okay? And you want, so the problem is that diseases are different because we want to impose, you know, flat relations. So we call this actually theta, this one. We want that, you know, tanh theta is lambda over d. That's what we do in, I don't know, high school. We want to maintain that same relation. We want to pretend that if we know the scale and we know the angle, we have something that's called distance. And that's the angular diameter distance that's showing a sphere, okay? Okay. On the other hand, you can do, okay. Good. So in CMB, we actually have a way to determine this, okay? So now, in flat space, I want to, this is actually D, this is approximately this. This is in flat space, but not in a sphere. If we know the Hubble function, and we just learn how to know the Hubble function, we know the density, we can calculate from today to Big Bang. Okay? Okay, so we calculate for today to Big Bang, and then, let me do it again. So we know this guy, and we know the redshift of this guy. So we know there's something at lambda at redshift of 1,000, sorry. That's the thing. So there's something at redshift of 1,000 that we know its length. So now you do this integral from redshift of 0 to 1,000, and we know the contents of the universe, so we can determine of dA. Okay? So we know this, and we know this, and when you do this calculation, and we're gonna do, you got 2 degrees. So far you say, so what? You have something that has a length, and this length is equivalent of 2 degrees. So far nothing. But the one thing that's we will learn in CMB, I hope we have time, is that this length that we can determine in CMB, it's actually the horizon that a photon can travel from Big Bang to the CMB. So, you know, so basically, suppose, okay, let's do another example. Suppose the universe has 10 years. And at 1 year, you know something distance at 1 year because we're observing the past. So we propagate how much light can travel in 1 year. Then you get the angular diameter distance from 1 to 10, and then you can get, you know, what is the horizon size in angle. And when you do this, it's about 2 degrees. That means that without something else, it's a miracle the universe looks isotropic. And this something else is inflation. So basically, so what's the solution? You change the horizon at between 0 and 1 year in this example. And what we do, inflation happens within the first second of the universe. And it's a process that exists to expand the horizon. So basically this. I will come back to this example in better detail. But But the question is, because the universe is finite, there's a finite distance that things can travel. And this finite distance without inflation is about 2 degrees.
I'm sure there are other questions.
Yeah.
Are you sure not? Okay. If not, let's thank. And now you have the flash talks, Marco.
Yes, now we're gonna switch quickly the PC, and then we have 3 flash talk: Diana, Eduardo, and Saulo. But we just need to